Now, previous lectures we mentioned a couple of times that the goal, our goal in this course, or one of our main goals in this course, is to develop systematic ways to solve a circuit. Okay? And by solving a circuit, we mean, given a circuit, figuring out all the currents and voltages throughout the network. We saw that the equations necessary in order to be able to obtain those currents and voltages, they come from two different sources. Okay, one set of equations are coming from the so-called network laws, okay, or Kirchhoff's laws. We have Kirchhoff's current law and Kirchhoff's voltage law. Okay, together they give half of the equations that we require, and the other half, we said, comes from the so-called terminal equations. Okay, so combining those two sets of equations, or those two sets of constraints, we can solve any circuit. Okay. Now, if you have a very simple circuit, say that's made of 3 or 4 components, let's say, then what you can do to solve it is just write whatever you can write using KCL, KVL, and terminal equations. Since the circuit is very small, there won't be many equations to deal with, and somehow you can figure out the answer. Okay? But if you have just a few more components, or generally speaking, for an arbitrarily large circuit, just writing down whatever we can write is not the right way to go, because things will get very messy very rapidly. Okay, so therefore it's essential that we have some method to attack the problem of solving a general circuit. Okay. So today we will do that. In fact, today we're gonna take the first steps, okay, toward achieving that goal, that is, toward developing a systematic approach for solving a circuit. So it turns out that that requires, for a given circuit, to first obtain its graph. Okay, so that's what we're going to see today. Given a circuit, its graph representation. What's its graph representation? And once we have the graph, we will be able to obtain the equations that are imposed on the circuit by KCL and KVL. Okay, and once we have the method to write down those equations in a systematic way, then the rest will follow. Eventually, we will introduce terminal equations into the picture, and we'll have a proper formulation of the circuit from which we can obtain the solution. Okay. So once again, in today's lecture, we're gonna be talking about first the graphs of the circuits, and then by looking at the graphs, we will see how we can write down the equations in a regular way, coming from KCL and KVL, and also along the way we will discover one of the very important, perhaps the most important theorem in circuit theory or in network theory, namely the Telegraph theorem, which has a very short and elegant proof. Okay, so let's now talk about what we mean by a graph for a given circuit. Systematically analyze circuits, it turns out that working with their graphs is very beneficial and time saving. Okay, we study their graphs. Okay, so the question now that we have to answer is what we mean by a graph. Okay, graph is a very useful pictorial visual tool that comes from mathematics, and for a given circuit we obtain this graph as follows. Suppose that this is our circuit, with 1, 2, 3, 4 nodes and 5, 6 components, okay, 6 branches. Let's call this circuit N. Okay. Now our goal is, from the circuit we obtain graph, and from the graph we formulate KCL and KVL for this graph. Since KCL and KVL, they only care about Kirchhoff's current law and Kirchhoff's voltage law. They only care about the connections, who is connected to whom. Okay, they don't care about the intrinsic properties of the component. Therefore, we don't have to be specific about whether this component is a voltage source or resistor or capacitor. Okay, all we need to know is who is connected to whom, who is the neighbor of whom. Okay, therefore, we just represent our components by this simple rectangles, okay? Because we don't care about their intrinsic properties. Or in other words, at this stage, we don't care about the terminal equations, okay? So this is our circuit N, and from this circuit, what we want is, we want to obtain its graph. Okay. So the procedure is as follows. First, label each branch. Okay. Now, note that all these components are two-terminal or a single branch components, and by a branch, each of these components now, when we talk in terms of graphs, we represent them by a branch. Okay, so label each branch. Okay. Then assign a direction to each branch, and that direction is arbitrary. Assign an arbitrary direction to each branch. Okay. Once the labeling and giving directions to branches are complete, we also label the nodes. Okay, label each node. And then once all the labeling is complete, our graph is ready. Okay? For obtain the graph. Okay. Now what we mean by this procedure is as follows. Okay. So let's start with that circuit over there. Now this is our circuit, and the same thing here. Now what we do is, first we label each branch. Okay, labeling means just give it a number or give it a letter. Okay, let's do with numbers. 1, 2, 3, 4, 5, 6. Okay, it's just arbitrary. This is our first branch, second branch, third branch, and so on. And then once that labeling is complete, we also assign a direction to each of those branches. Okay? This is the direction for branch 1. It's arbitrary, okay? It could have been the other way. I'm just assigning directions arbitrarily. This is the direction for the second branch, for the third branch, fourth branch, fifth branch, and let the direction for the sixth branch be as such. Okay, so first step is complete, second step is complete, and then we now have the third step, label each node. Okay, we have 1, 2, 3, 4 nodes. Let's label them as 1, 2, 3, 4. In order to avoid confusion, let's put a circle around those numbers so that we know that they indicate a node, not a branch. Okay. So we have the node labeling complete, and that means now we're ready to obtain the graph. You can take this as your graph, but since we don't need those rectangles anymore, we can do with a much simpler picture, a much simpler figure. Okay. Therefore, the graph of the circuit N is this. So basically a graph is just a set of nodes that are connected by branches. Okay. So we have 4 nodes and we have 6 branches. Okay. So that's the graph representing this circuit. Of course we have to also put on proper labeling, which we did here. So we have 1, 2, 3, 4. Those are our nodes. And we have 1, 2, 3, 4, 5, and 6. Okay. And those are our branches with the assigned directions. So this is our graph. So that graph has 4 nodes, which we labeled as 1, 2, 3, 4. Okay, that's our node set. And it has 6 branches, which we labeled as 1, 2, 3, 4, 5, 6. Okay. For instance, the second branch is this one that connects first node to third node, and its direction is from first to third node, and so on. Okay. Now for our later general discussion, let's introduce some notation here. From now on, we're going to call number of nodes with n. Okay. And in our case, n equals 4 because we have 4 nodes, and number of branches for a given graph or for a given circuit, we're going to denote it by letter B. And for our particular example, B is 6. Okay. Now everything is nice and easy for such a circuit where every component is two-terminal. But we have seen that there are components in circuits that are 3 terminals, or they have more than 3 terminals. Okay. And then the question is, since they are not single branch components, how to represent them in a graph. Okay. So let's talk about that general question, and then we can move on to KCR representation of a given circuit. How about the below circuit? Okay. We have here a single branch component. We have here another single branch component, which we're perfectly okay with. But suppose there is also a 3-terminal component. Okay. Suppose that this are simple circuit. Simple, but not that simple because it has a 3-terminal component. How to obtain the graph representation of this circuit? Okay. So there's no problem with labeling the nodes. Suppose that we label the nodes as 1, 2, and 3. We have 3 nodes. And there's no problem with labeling the 2-terminal components. Let's call this 1 and let's call this 2. Okay, and now here comes the question, how to represent this 3-terminal component in a graph. So what you do is as follows. When we have a K-terminal where k is 3 or larger element, we assign one of its terminals or terminal nodes as reference and then treat it as k minus 1 single branch elements. As follows. Suppose that we have this component here drawn separately with nodes 1, 2, and 3. Okay. Now, let's choose the second node, just arbitrary choice, as reference. Okay, this is an arbitrary choice. Okay, and then when we're drawing the graph of the circuit, this component is represented by 2 branches. One branch is from the first node to the reference node, the other branch is from the third node to the reference node. Okay, so that means in its graph representation, 2, 1, 3, from 1 to 2, from node 1 to node 2, we have a branch, and from node 2, from node 3 to node 2, we also have a branch. Okay, so 3 terminal component is represented in its graph by 2 branches, 3 minus 1, 2 branches. Okay, okay, so let's give numbers to them. Suppose that this is our 3rd branch and this is our 4th branch, and the directions are again arbitrary. Okay, so we have the 1st branch, 2nd branch, and this is represented by 3rd and 4th branches, and now that means we're ready to obtain the graph. Then graph of the original circuit. Becomes, okay, this is our original circuit. Okay, we have 1, 2, first and second branches for the single branch components, and we have 3rd and 4th branches for this 3 terminal component, and one, 2, 3, and we have the graph. 1, 3, 4, and 2. Okay, and the directions are again all arbitrary. And for K terminal component, we have Suppose that this is our K terminal component, and in its graph representation, it can be represented as, choose one of those K nodes as reference. Suppose that we chose the K node as reference. And then what happens is, from all the remaining non-reference nodes, we connect to the reference node with a single branch. Okay, 1, 2, K minus first. Okay, so that's how we deal with 3 or more terminal components. Now, once we have the graph, which we obtain from a given circuit, it's very easy to obtain equations imposed on currents, let's say, by KCL. And we're going to now see how we do that. Let's return to the very first example, which was for this graph with 4 nodes and 6 branches. Okay, and this was the labeling 2, 3, 4. We had 4 nodes labeled as such, and we had 1, 2, 3, 4, 5, and this was the 6th branch. Okay. Now let's write Kirchhoff's current law, or the equation that's imposed by Kirchhoff's current law at each node. At each node. Okay. Now we can obtain the matrix formation for KCL. Okay. So we go node by node. Since we have 4 nodes, that means we can write 4 equations. Okay. At node 1, at node 2, at node 3, and finally at the 4th node. Remember what KCL was for any given closed surface. The sum of incoming currents must equal the sum of outgoing currents. Okay. For instance, for the first node, we have 1 and 2 that are outgoing and 6 that's incoming. Therefore, 1 plus 2 equals 6. Okay, by KCL. So that's the equation imposed on the currents associated to node 1, okay, by KCL. Okay. Now, to obtain the matrix in the end in a proper fashion, what we're going to do is we're going to stick to some convention, okay, and that convention is as follows. We're going to treat all the currents as if they are outgoing, okay. And how is that possible? This is outgoing, okay. 1 and 2, there's no problem with that. But this 6th current, I6, is incoming. How can we treat it as an outgoing current? All we have to do is reverse in our heads the direction, okay? Now, if I6 is incoming, then minus I6, we can treat as the outgoing current. And in that case, since all the currents are outgoing and there's no incoming current, then that sum must equal to 0, okay? So, I1 plus I2, outgoing, plus minus I6, outgoing must equal 0. Okay, so that's the first equation for the node 1 by KCL. Let's do the same thing for the second node. We treat everything as outgoing. Now I1 and I3, they are incoming, and I4 is outgoing. Okay. If I1 and I3 are incoming, therefore minus I1 and minus I3 must be outgoing. So what we have is minus I1 plus minus I3 plus I4, all outgoing currents must equal 0. Okay. And then the third node, we have minus I2 plus I3 and plus I5 equals 0. And finally, at the last node here, minus I4 minus I5 and plus I6 must equal 0. Minus I4 minus I5 plus I6 equals 0. Okay, let's call this set of equations star. Okay, now let's put those 4 equations into a single matrix equation. Okay, because once we express things in terms of matrices, certain things become easier to notice. Okay. Equations star here, the equation that you obtained by KCL, can be written as or rewritten as some matrix, okay, times the vector that you obtain by stacking all individual currents into that tower, into that column, and we have the right hand side, and the right hand side is all zeros. Okay. Now, this will be our current vector or branch current vector. Let's call it I. Okay. So we have 1, 2, 3, 4, 5, 6 currents. So that means the entries of our current vector will be I1, I2, I3, I4, I5, and I6. Okay. And this matrix will be such that to each node there will correspond a row, and to each column there will correspond a branch. Okay. So the first row is assigned to first node, second row to second node, and so on. Okay. So it's going to have 4 rows and 6 columns. 1, 2, 3, 4, 5, and 6. Okay. Now the question is, what are the entries of that matrix? Okay. Now the entries of that matrix will be directly coming from these equations that we wrote using KCL. For the first row, which is assigned to the first node, we'll get the first equation that we wrote here. Okay. Which says I1 plus I2 minus I6 equals 0. So I1, I2, here we have 1, 1, and minus I6, that means we have minus 1. And since we don't have any I3, I4, or I5 that appears in this equation, that means the corresponding coefficients must be 0. Okay. And the right hand side is 0. That's why we have a 0. Note that this equation here is same as multiplying this row vector with this column vector. Okay. This row times that column gives us I1 plus I2 minus I6 equals 0. Okay. Now we're going to do the same thing for the remaining rows or remaining nodes. For the second row, we look at the second equation. We have I1, I3, and I4. That means I2, I5, and I6, they don't appear. 2, 5, and 6, they have 0 coefficients. And we have for 1, 3, and 4, for 1 and 3, we have minus 1. Minus 1, minus 1. For I4, we have plus 1. Okay, and the right hand side is 0. Okay. For the third equation, we have no I1, minus 1 for I2, plus 1 for I3, no I4, 1, 4, I5, and no I6. Okay. And finally, for the last row, we look at the last equation. We have no entry regarding I1, I2, and I3. And for the remaining three currents, we have -1, -1, and +1. Zeros. Now, this matrix is important. Therefore, let's give it a name. Let's call it A sub A. Okay. It has a name. It's called incidence matrix. AA is called incidence matrix. Okay. In our case, it's a 4×6 matrix, but in general, it's N/B matrix. Remember that N was the number of nodes we have, and B was the number of branches we have. Okay. It's an N/B matrix, and it's more or less clear how it's obtained by looking at this simple example. It's obtained as follows: Aij, this is the ijth entry of our incidence matrix. Ijth entry means that the entry corresponding to ith row and jth column. Okay. The entry is +1 if the jth branch leaves ith node. Okay. First branch leaves first node, second branch leaves first node, and the sixth branch is incoming, it's going into the first node. Therefore, these two guys are +1, and since this is going into the node, it's -1. And all the other branches that doesn't touch that particular node, the coefficients are 0. Okay. So -1 if jth branch enters ith node, and if the branch doesn't touch that node, then the corresponding entry is 0. 0 otherwise. And I, this is our incidence matrix, and I, in general, is our branch current vector. I is branch current vector. I is I1, I2, IB. In our case, B was 6, therefore it's a vector of dimension 6. Okay. Now it turns out that all the constraints imposed on the currents by KCL are in this set of equations, okay, or in this equation, in this matrix equation. Okay. Now the question is this the most economic way of expressing those constraints imposed on the currents by KCL? Okay. It turns out that it isn't. Okay. There's a more economic way. There's a minimal way of expressing KCL, and for that, all we have to do is we have to realize that the rows of this matrix are not linearly independent. Okay. And for that, let's remember linear dependence or linear independence, and then once we remember what linear dependence or independence was, we can express KCL in a little bit more economic way. Okay, by redefining the incidence matrix. Okay, so let's remember what linear dependence was. let V1, V2, Vk represent some k vectors of the same size. Vk vectors, all same size. If we can find real numbers, alpha 1, alpha 2, alpha k, such that, and at least one of them is different than 0, not all 0, such that alpha I, Vi equals 0. That is the sum alpha 1, V1 plus alpha 2, V2 plus and so on, up to alpha k, Vk. If that sum gives us 0, and at least one of those coefficients are different than 0, so that means this set is a linearly dependent set. Okay. Then vectors V1, V2, Vk are linearly dependent. Okay. Otherwise, they are linearly independent. Linearly independent. Okay. Example. Consider this set of two vectors in R2. One is 1, 0, the other is 0, minus 1. It's obvious that these two vectors are linearly independent. Okay, are linearly independent. Okay. However, whereas 1, 2, 3, 4, 5, 6, and 7, 8, 9. Consider this set of three vectors. Okay, let's call them V1, V2, and V3. It's not obvious whether they are linearly dependent or independent, but it turns out that they are linearly dependent. Okay, are linearly dependent. Because we can find alpha 1, alpha 2, alpha 3, and at least one of them different than 0, so that alpha 1, V1 plus alpha 2, V2 plus alpha 3, V3 equals 0. In fact, you can let alpha 1 to be 3, alpha 2 to be minus 6, and alpha 3 to be 3. And if you sum those three vectors, you see that they give you 0. Okay, having remembered what linearly independent vectors or dependent vectors were, now let's return to our matrix formulation and concentrate on the rows of the incidence matrix. Okay. Now, since we were careful about writing our KCL equations, we stick to the convention in such a way that we treated all the currents as if they're outgoing. That sticking to that convention gave us, made it obvious that the rows of the incidence matrix are linearly dependent. Why? Because there's exactly 1 plus 1 and 1 minus 1 at each column. Okay? So that means if you sum those four rows, okay, let's call this V1, V2, V3, and V4. If you sum all those four rows, since there's exactly 1 plus 1 and 1 minus 1 at each column, the sum will give us 0. Okay? Since the sum gives us 0, so that means those rows are linearly dependent. And when we have linearly dependent rows in such an equation. So that means the individual equations that are coming from that matrix must be redundant. Okay, it must be superfluous, meaning that there's a more economic way to express KCL in this case. Rows or row vectors of AA, our incidence matrix, sum up to 0. Okay. Therefore, those rows are linearly dependent. So what we do is, to express KCL in a minimal way, we choose one node as reference, and then we remove the corresponding row. And remove the corresponding row from the incidence matrix. The new matrix has a smaller size of size n-1 by b. Okay, remember n was the number of nodes in the graph. It's called the reduced incidence matrix. Okay, and denoted by just an A. We now get rid of that subscript. And denoted by just A. Okay. Now let's apply this suggestion to our example. Okay, so AA is over there. Let me rewrite it. And then 1 minus 1, 0, 0. 1, 0, minus 1, 0. 0, minus 1, 1, 0. 0, 1, 0, minus 1. And minus 1, 0, 0, 1. Okay. Now, since the rows are linearly dependent, what we do is we choose an arbitrary node and remove the corresponding node. Let that arbitrary node be the last one, node 4. The corresponding row is row 4. Therefore, we're going to remove this row, okay? And what we will be left with is a 3 by 6 matrix. And that new matrix we're calling the reduced incidence matrix. So let node 4 be the reference node. Okay. And then reduced incidence matrix is simply 1 minus 1, 0, 1, 0, minus 1, 0, minus 1, 1, 0, 1, 0, 0, 0, 1, and minus 1, 0, 0. Okay. Now, rows of A turn out to be linearly independent, provided that the graph is connected. Okay. Rows of A are linearly independent, and that they are linearly independent means that you cannot remove any further rows without losing information regarding KCL. In other words, A times I equals 0 is the most economical way to express KCL. Linearly independent if graph is connected. Okay. And such A, whose rows are linearly independent, is called full row rank matrix. Such A is called full row rank. Okay. Now, of course, we have to be clear about what we mean by a connected graph. It's more or less self-evident, okay, what the connected graph means, but for the sake of completeness, let's put the definition down. Definition is as follows. The graph is connected if there is a path. Okay. And when we talk about paths, let's at this point forget about the directions of the branches, disregarding the direction of branches. Connecting any two nodes. Okay, in the graph. For instance, consider this 4-node and 4-branch graph. This is connected graph because you choose any pair of nodes, you can find a path that connects one to the other. For instance, let this be node A, let this be node B, and then from this node to that node, and from that node to B, you can construct that path. Okay. A path from node A to node B. Okay. Likewise, for any other pair, you can clearly see that there is a path. However, this thing, considered together as a single graph, is not connected because, well, from this node to that node there is a path. From this node to that node there is a path. But from this node to that node there does not exist a path. Okay, because that graph has two separate components. Therefore, that's a non-connected graph or disconnected graph. And by graph we mean this together as a single graph. Okay. So let's return to KCL, or the incidence matrix. Hence, for a connected graph, at least, or for a circuit with a connected graph, to write KCL or all the equations coming from KCL in minimal way, what you do is you construct the reduced incidence matrix, which first you can construct the incidence matrix, and from that just eliminate an arbitrary row, and what remains is the reduced incidence matrix, and that matrix times the current vector equating equal to 0 is all the contains that equation contains all the constraints imposed on the circuit currents by KCL. Hence we obtain the minimal expression of KCL. A times I equals 0. Okay, this is KCL. And A is, for a connected graph, n minus 1 by B matrix. Remember, n was the number of nodes and B was the number of branches. And this is our reduced incidence matrix. And I is a vector of dimension B, B number of branches, is the branch current vector. Okay. So in our next lecture, we will study the relation of the reduced incidence matrix to KVL, in particular to node voltages, and then we're gonna go and try to formulate KVL in a minimal way.